Okay, I'm very pleased to introduce Erling Hedkvist, evidently the one and only Erling Hedkvist. and he's going to be talking to us today about dealing with limited bandwidth and how do you get back videos from remote venues. So we're really looking forward to this. Thank you.
Thank you, Wes. Thank you so much. Thanks for having me, everyone. Thanks for coming to listen to this little spiel. So remote production unlimited. We're going to talk about two different approaches for coping with remote production. As we all know, remote production is very hot right now for the purposes of these reasons. Doing more with less, cost efficiency, we can all sign up on that. Higher utilization is of course the ability to centralize equipment to use it more efficiently. I remember a customer in the US, they had their own facility, and they did an analysis of how much of their equipment in their basement, basically their broadcast equipment, was used at any one time, and the ratio was around 20%. So they're sweating 20% of their assets. Of course, one thing you want to do is use this equipment more frequently and thereby using it for more productions, and that's what centralized production is all about. So productions are happening all the time, but instead of sending equipment out to that, use the equipment down in a centralized area and send the cameras remotely. I think we all know this is kind of old news at the moment. Other reasons, the move to 4K, 8K, different audio formats, etc. We all know about it. Users expect multi-purpose solutions, etc. So this is well known. So let's look at the two different approaches to remote production. As from the previous speaker as well, talking about compression. So compression is a necessary evil, if you will, if we don't have enough bandwidth. And any codec on the market, whether it's the VC2 Plus or JPEG-2000 or whatever codec might be, has basically three aspects that we're looking into, and that's latency, quality, and bandwidth. And these three characteristics is what defines what the codec does. So you're looking for something that has very high quality, uses up as little bandwidth as possible, and has as low latency as possible. The reasons for quality, I think everybody understands. I mean, of course, if you're going to do a remote production, you want to have a high quality on your codec. The reasons for latency is, of course, if you truly want to do a remote production where the technical director, the audio mixer, etc., sits remotely, you have to work with the delay that is introduced that makes the production more difficult. And then bandwidth. The lesser the bandwidth is, the more you can compress this, then of course you can use cheaper bandwidth links. So we're looking for a codec then in a remote production application that allows for very low latency. So we're able to put the cameras remotely and still have a director talk to the cameraman remotely and cut when the new player gets the ball or whatever it is. So it's not a 1 second delay before the camera guy hears it or that the TD sees what's going on. And we also need to have the quality there to, of course, allow for multiple encoding passes, etc. So this brings us to codecs that are in what I call the mezzanine compression range. So again, if you were here for the previous presentation, which I only caught the last bit of, we're looking at compression ranges between, say, 2:1 to 10:1. So what kind of codecs is that? So I just found out about this new one, this VC2 Plus. But other than that, is JPEG-2000, which has been around on the market for a long time. It's a well-known and standardized codec, J2K Part 1. There's also, of course, some standardization work being done in the VSF forum with TR01. Now in the 2018 revision of that standard for interoperability of JPEG-2000 between different manufacturers. So that's one codec that's been around for some time. Another one that's been around for a long time is the VC2 or the direct codec. That's a more lightweight codec than the J2K codec, so it's also therefore faster. You're looking at somewhere around 20 lines as opposed to half a frame or a frame, depending on where you are on the J2K spec. Originally developed by BBC, royalty-free. Parts of it, or part formats, are standardized in SIMD 2042. Others are not. And then you have TICO, which also has been around for a little bit. Stands for Tiny Codec, developed by Intopix. So these three, I would say J2K, VC2, and TICO are the ones that we've seen deployments of. I would say out of these three, J2K is by far the most heavily deployed. It's also the one that gives you the most compression, but it has the longest latency. Now there's low latency versions of J2K, but when you go down to that, it becomes a little bit more vendor dependent, to be honest. And then there's the two new guys on the block. As I said, I just missed the previous presentation a little bit, but seems to be one more now than with VC2 Plus, which I'm quite interested in reading more about. But the ones I know about is JPEG-XS, and there's a lot of buzz around that one at the moment. JPEG-XS is a new JPEG standard, so it's not a part of JPEG 2000, so it's a completely new JPEG standard. It was designed to, it stands for extra small, I believe, or extra fast. It was designed to be able to be run in small FPGAs and also on CPU, pushed by Fraunhofer and Intopix. And the purpose is really to get the compression ratio of a JPEG 2000, so like a 10:1 ratio, but the speed of a VC2. So you kind of like the best of both worlds. And the other one is an extension of JPEG 2000. So this is JPEG 2000 part 15, which is called high throughput J2K. So high throughput J2K is, again, based on JPEG 2000, and they're looking for the same attributes that JPEG-XS is looking for. So you're looking for a higher compression ratio, and you're looking for much faster or lower latency, if you will. So my understanding with high throughput J2K is that you're looking for a speed that's in the 20 lines space. The compression is about maybe not 10 times, but 8 times, and backwards compatible to J2K. Excuse me. Right, so these are some of this is one variable or one version you can do as an approach to remote production. And the other approach, which I want to talk about, there we are, is what I call the next logical step after compression. So the first thing we've done is that we're IP networked all our devices. So that's already happening. We got SIMD 2110 and the SIMD 22 standards, etc. And the thing we did after that is to work with software defined, right? So I think pretty much every manufacturer now is saying that, hey, we have this one hardware, you load different softwares on it, and it becomes something new. So I would like to claim that the third thing here that we want to do is to have blades become processing clusters. So what I mean by that is, again, this is nothing new that the broadcast engineers or broadcast world has come up with. You can already see this being prevalent in the IT space, is that of distributed processing, right? So the concept is that you have a group of hardware that work of processing, where you talk to a cluster master and says, I'm looking to do this. I'm looking to do this much frame syncs and color space conversions and compression and whatever it is. And you tell this master device, this is what I want to do. It takes that task and it distributes the load across a cluster of cards that it defines of what to do. So it will do the job for you. You can kind of think of it as almost like a middleware, right? So you tell the equipment what to do, No, I'm good, thank you. So one of the benefits of this is that in a cluster environment, you have automatic redundancy because the master distributes the work across all the processing nodes. So if one node dies for whatever reason, the master sees this and just distributes the load somewhere else. Again, this is not something I came up with or something. This is, I think, is a logical step for the broadcast space to also go into, which is very similar to the distributed processing that we see for example, for web servers or firewalls, etc., using Kubernetes and other microservices, right? So what are the benefits? Replaceable instances perform a given task. So all you really care about is that this is the total amount of work I'm going to do. And the system will decide what is the necessary processing capacity required to do it. So it becomes very dynamic. It's inherently self-healing, right? So if a device dies, even if the master dies, any of the other cards can then become the new master. Similar to what we see in SIM2 2059 or PTP, basically, where you have a best master that just a new master gets assigned if the other master dies. Also makes it very easy for the control system, which you undoubtedly going to have, that just talks to one card and it tells this, or one node, doesn't have to be a card, could be a process unit, and then distributes the work. This is really good. You can really get into this elasticity because you can just say, well, this production I'm doing now, or this amount of production I'm doing now needs this. I need less of that and more of this, and the system will just basically scale up and down as you need to. And because the system will give you feedback of how many processing cores are needed to do this job, and all the cores are software definable, you can simply just add or remove cores as you need. So it's easy for you to, again, get higher utilization of your facility. Ability to prioritize. So now we're getting to kind of really squeezing the most out of the system. Let's say you're running at the edge. So you have this process, you're running 5 control rooms at the same time or whatever it is, and you're using all the processing power there. You can prioritize and say, well, these services are more important than these services. So in case there is a failure, the system can then say, well, this is the lowest priority, so these services are simply not going to be done, but these services can be done. I see that, for example, in master control environments when they say, well, our program feeds always have to be there. If there's some monitoring going on somewhere else, that's not as important if I really need to make the choice. Automatic load balancing. So of course the system's going to spread the load out across the entire cluster. And I mentioned this earlier as well, easy management via a master. So it makes the role of the controllers much easier. Instead of talking to 1,000 devices, it talks to one process. And this process can also scale. So the master process itself that distributes all the work doesn't have to sit on a particular hardware blade. It can sit on a process unit in a server blade, for example. It's totally possible as well. This also means freely mix and match. So all you really care about is the total aggregate capacity of your cluster. If you connect 10 gigs, 40 gigs, 25 gigs, 100 gigs, all this stuff, of course, the more you connect it, the better it is. But you don't have to say, I'm getting out 25 gig, is this an important thing for me now, or 40 gig. You just can connect as much as you want. And the aggregate capacity of your bandwidth and the aggregate capacity of your processing cluster is what really matters. And of course, I have to do the kind of the Lawo pitch now then of how this fits into what we're trying to do. And the example is our what we call the distributed multiviewer, right? So we have a product that is uses this concept. It's called the distributed multiviewer, or the DMV. And it's basically a software app that runs on a software-defined blade, and it uses this master-slave concept. So when you build your multiviewer, You can first just put processing blades wherever you want them, in the same building, in different buildings across the world, doesn't matter. Well, what matters is, of course, the speed of light latency if you put stuff across the world. There's nothing we can do about that. You can't break the speed of light. But the total aggregate capacity is what matters. So you tell the system, I have this many SDI sources, IP sources of this capacity, and they're added into basically a database. So you can have thousands, hundreds of thousands of sources in this database. And then you tell the system, I am looking for this, this output. So an operator cares about output mosaic on a head. So how the system works inside is that you have, let's say, 1,000 sources. These sources are divided up amongst the processing blades. They're all connected on IP. That's a prerequisite for having a cluster. So these sources might come in over SDI or over IP. So if they're in SDI, that processing card has to be the one that processes it. If it's an IP source, any of the processing blades can do this. And what we do is we create something called MIP maps. So a MIP map stands for multi-mean param, which is a fairly old, from the 1960s or so, mathematic formula that takes any size raster and creates exactly one quarter size raster of that. Incredibly fast. So what we do is we take whatever size source you have and we create multiple of these MIP maps. So let's say, for example, you take a 1080p source, okay, a 3 gig source. Then I will, a little bit less than 2110. Then I will take and make a quarter resolution. This processing card will make a quarter resolution of that, and then a quarter resolution of that, and another one, up to 4 levels. So you have a quarter size, 16th, 64th, and 256 size, okay? And it just takes these sources, processes these MIP maps, and sends the MIP maps back into the network. So now you have your original source, and you have 4 sub-resolutions all available inside the cluster. The next thing that's going to happen is that as an operator, you say, well, I want to have source 1 there in this size and source 2 at that size, and whatever the mosaic you want to be, right? The master card gets that information, and it says, well, card number 43, you're not doing anything at the moment. You build this output head for this operator. And the card 43 then is going to subscribe to the most appropriate sized sub-resolution that fits the mosaic layout that the customer, the operator has requested, and it's going to do the final resizing. It's also going to add PPM information, graphic, tally, and all this stuff, and then output that as an IP stream or over SDI. So with this concept of spreading out the pre-processing, sending the pre-processed information back into the cluster, into the IP network, and then being able to subscribe to just what you need that's appropriate to create the output head, you build a multiviewer that is distributed, which you can scale infinitely. It doesn't matter if I wanted to build an output head that has 128 4K sources on a 1080p monitor, there's no problem doing that. To try to do that in one blade, to get 128 4K sources into one processing blade, it's not anywhere near term. Just the processing capacity to do that alone exceeds military-grade FPGAs. So the only way to really scale is to do this distributed processing. And that's what we think is a natural next step for remote production as well. So you start with your IP connectivity of everything. The next step, have software-defined functionality for your blades. And the third natural step is this pre-processing and distributed processing of your facility. So this doesn't just have to be for multiviewer. You could do the same thing for color correction or frame sync or audio shuffling or whatever you want to do. You could tell the system what it needs to do, and the master can go out and distribute that particular function to any card, even upload the correct software is required to make it happen. And we think those two approaches are the right approaches for remote production. Yeah, so this is all, of course, based on the fact that we now have IP connectivity everywhere, so we can have these processing clusters close to each other across a wider network, I mentioned again that one of the benefits is that you get this M plus N style redundancy for everything that you do. So you have immediate backups. And this is just a little bit of visualization of how this is done. We allocate processing units to a cluster. This is basically hardware blades. Then we assign tasks to those clusters, which might be frame sync, color correction, or whatever it might be. And thirdly, because these devices themselves are software definable, what they actually do themselves can be defined in software. That is 23 minutes, Wes. So if there's any questions, I'm happy to take them.
Okay. So thank you, Erling. So do we have any questions? Yeah, go right ahead.
I just wondered what the effect would be, in your opinion, of the sort of unpredictable latencies that might creep in when you don't know exactly where various processes are going to run at any given moment necessarily.
I think that's a design aspect. So in practice, what we've seen is that we know it depends on the processing function itself. So for example, we're doing the multiviewer is sub 4 lines latency for creating the MIP maps. So we don't the biggest issue there is really the transmission latency across links if you want to truly distribute, and therefore in the case of the multiviewer application, it becomes a design choice where the customer would basically say, well, what kind of latency are you okay with? For live production, which is kind of the Lawo thing, 1 frame total is the max, so therefore you kind of have to build stuff around that. Now, different processes will have different latency. Of course, if we talk about having compression as a cluster, then if your compression happens somewhere else, then we'll. So I think it depends on the processing function that's going to happen, and then it becomes just a choice from a design perspective when we build a project with a customer. I can't see why this wouldn't be with multiple vendors at the same time. Or really, where do we want to put our processing to have this work for us? Yeah.
Question? Hold on.
Hello, very good morning. With respect to low latency, like what is the target level that we can achieve here? And is it based on something like CMAF LLC, or can you just throw some light on that?
Yeah, so the latency at the moment that I see is that the end-to-end latency is 1 frame, right? So if you look at CMAF, all this stuff can be configured and chosen depending on your network latency. You need to, anytime you send something over an IP network, you lose timing, right? So you have to reconstitute timing at the other end. So then the question is just, CMAX is all about, okay, what am I capable of buffering, or how much do I have to buffer to feel confident that I'm going to be able to handle the jitter in the network? And whatever that time is of course, is the additional latency you added. Now, in reality, what you can't really get around an end-to-end latency of 1 frame. Because as soon as I send something on the wire, I can't receive it at the same time as I'm sending it. That is physically impossible, which means that you introduce, as soon as you do anything, you send something, it will be late arriving at the other end. Now, but you have a full frame of time that you can do things with. So you can, I think that one of the benefits of IP is that we should only reconstitute timing at the output end. So everything in between can be done in the IP space. So we can have processes come in between where we receive something. We don't have to frame sync it there. We don't have to get it back to a particular time there. Process it, introduce more delay, whatever it is, another 20 lines, 5 milliseconds, whatever it is. Do another process, another process, another process. And when you're done through all your processes, compression, color correction, up conversion, whatever, you've added 18 milliseconds, whatever that is, right? And then now when you're ready to put that out to play at wherever the timing needs to begin, and now we frame sync again, and now we're at the right time. What I see people do sometimes is that they tend to want to get back in time for every processing step, and therefore by default add a frame of delay at every processing step, and it's simply not necessary in an IP space to do that. You can clock, you need to reconstitute timing anyway. You receive something, get it back to the video format or the audio format, do your processing, send it back out again. Forget about what the global timing is at this point. Process, 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 incur delay, incur delay, incur delay. And now when you're finally done, you reconstitute timing, and there you should only be a frame later. So.
Okay. Erling, thank you very much.
Thanks, Wes. Appreciate it. Appreciate the opportunity. Thank you.
And just to remind everybody, if you want a link to the presentations, scan your badge at the entrance. And the videos will be posted at vsf.tv as soon as we possibly can. So we'll start with our next presentation in about 2 minutes.